Hi, this is the Science Chef. We'll be continuing with our solutions to the October-November 2019 Cambridge IGCSE Chemistry Paper 4. Today, we'll be answering question 3. If you'd like to watch our solutions to questions 1 and 2 of this paper, kindly check the links in the description. Also, join our membership club to gain access to exclusive videos, live chats, and our live tutorials. So let's start. Question 3. Question 3 says, ammonia is an important chemical. Let's underline the keyword. The keyword here is ammonia. This question is on ammonia, right? Then says, ammonia is manufactured by the Haber process. Haber process industrially. The production of ammonia industrially is known as the word Haber process from nitrogen and hydrogen at certain world conditions that we'll be looking at later. Okay. The reaction is reversible. The reaction is reversible. Okay. What is the sign for a reversible reaction? Okay. Sign for a reversible reaction. So first off, what is a reversible reaction? A reversible reaction is any chemical reaction that can occur in both directions. That's both forward and backward directions under suitable conditions. And most times, let's say if this is a chemical equation, A plus B giving us what? C plus D. This is a one-directional chemical equation. Now, for a reversible reaction, it will have to occur in both reactions. So it goes forward and comes backward under suitable conditions, which means that at the point as the reactants A and B are combining to give product C and D, C and D are combining again to decompose back to A and B. So that's a reversible reaction. Now if you check these two arrows, you can see that for a one-directional reaction, a reaction that goes to completion, right, the arrow has two heads. The head of the arrow is complete, right? Whereas for a reversible reaction, the head of the arrow is not complete. So the forward reaction arrow has a half head, while the backward reaction arrow has a half head, to show that the reaction is a reversible reaction. So this is the sign. This is the sign for reversibility. So you do this forward and backward. So that's the answer, right? The next question says, state the essential conditions for the manufacture of ammonia by the Haber process starting from hydrogen and nitrogen. Include a chemical equation to show the reaction which occurs. Alright, let's underline some keywords here. That has to do what? To state the essential conditions, right, for the manufacture of ammonia by the Haber process starting from hydrogen and nitrogen, and you should include a chemical equation to show the reaction which occurs, right? So now let's quickly go through Haber process. Haber process is simply the process of preparing ammonia industrially, as we have already known, right? Now the raw materials for the Haber process are always nitrogen and hydrogen. Now the nitrogen is always obtained from the fractional distillation of liquefied air, right? It is part of the questions we answered in question 2, so you can check our question 2. There was a question there on how oxygen is obtained from clean, dry air, and I used that opportunity to explain the fractional distillation of liquefied air. Nitrogen and oxygen are obtained from the fractional distillation of liquefied air industrially. So this nitrogen here is obtained from the fractional distillation of liquefied air, while the hydrogen is obtained from the cracking of hydrocarbons like ethane, or it can be obtained from methane in the form of synthesis gas, right? It can be obtained from methane by reacting with steam and then passing it through more steam, something like this: CH4 plus H2O give us CO plus H2 is a balance. Let's see, this will be 3, and it's balanced. Then we can pass this CO plus 3H2 through more steam, right, to give us CO2 plus 4H2. So this 4H2 is used in the industrial manufacture of ammonia, right? So conditions for Haber process: 1, reaction must be what? Reversible. 2, the mole ratio of nitrogen to hydrogen is what? 1:3. And then 3, the temperature of the reaction, optimum temperature is 450 degrees Celsius. Then 4, the pressure reaction must occur at about 200 watt atm, and 5, in the presence of what? Catalyst. That's finely divided iron. So this is just a summary of the Haber process. So let's see. So state the essential conditions for the manufacture of ammonia by the Haber process, starting from hydrogen, blah blah blah. So include a chemical equation to show the reaction which occurs. So let's start with the chemical equation. So nitrogen gas combines with hydrogen gas in a reversible reaction to give us what? Ammonia gas. So if we balance this, there are 2 nitrogen atoms here, and here there is only 1 nitrogen atom. So what do? We need to multiply this by what? 2. Multiply this by 2. We must now have what? 2 nitrogen what? Atoms, right? But this now makes the hydrogen atoms to be 6, right? 2 times 3, 6. And there are only 2 hydrogen atoms. So how do we make this 6? By multiplying it by what? 3. So multiply this by 3. So the equation is what? Balance. So we consider one of the conditions in the equation of reaction, which is what? The reversibility, right? Then temperature. Then the reaction is what? It is an exothermic. Reaction. That's change in enthalpy is negative. Alright, so that's that on that question. And what's the mark here? We have 5 marks. How do we earn these marks? For each of these conditions, we earn 1 mark each, right? So 1 mark for temperature, 1 mark for pressure, correct pressure, 1 mark for the correct what? Catalyst. There may not be any mark for exothermic what? Reaction, right? Then 2 marks for the equation of what? Reaction. Then how do you earn the 2 marks in the equation of reaction? 1 mark for the correct product and correct reactant, and 1 mark for the sign of reversibility. So that is how the 5 marks are distributed. Alright, let's look at the next question. Question 3A says, name 1 raw material which is a source of the hydrogen used in the Haber process. We've already answered that. We've answered that here where we said cracking of what? Hydrocarbons. But now we are asked to name, so we can name a specific word. Hydrocarbon. We can say ethane, propane, or we can use what? Methane, right? Natural gas, right? So 1 raw material used here, natural gas, from which we get what? Methane. Or you can say ethane or any other hydrocarbon. Propane, etc. So anyone will serve the purpose. But for natural gas, take note that natural gas is not cracking. You don't use cracking to obtain hydrogen from methane. Rather, you obtain hydrogen from methane through the process of what? Synthesis gas, right? Whereas you can obtain hydrogen from the other hydrocarbons by cracking them. So that's the major difference. Question 3b says ammonia is a base and reacts with sulfuric acid to form the salt ammonium sulfate. Let's underline the keywords here. Ammonia is a base, reacts with sulfuric acid to form the salt ammonium sulfate. Fine. Now we already know where the examiner is going. This question is on neutralization, right? Because the base is reacting with an acid to form what? A salt. What is meant by the term base? Base there are three concepts for the definition of what? Of a base, right? Or acids and what? Bases. We have the Arrhenius concept, we have the Bronsted-Lowry concept, and we have the Lewis concept, right? But your IG syllabus is focused on the Bronsted-Lowry concept, so not dwell in other concepts, right? So just focus on the Bronsted-Lowry concept, which defines a base as a proton acceptor, while an acid is a proton donor. So a base is a proton acceptor, while an acid is a proton donor. Because when an acid dissolves in water, it produces hydrogen ion as the only positive ion. That's according to Arrhenius, right? And that hydrogen ion is also known as what? A proton. I've already explained in one of my videos on these solutions why the hydrogen ion is considered as a proton, right? So try and watch our solutions to the questions on May-June 2020. I've explained that there. Fine. So a base is a proton acceptor, while an acid is a proton donor. Let's continue. Then name the industrial process used to manufacture sulfuric acid. The industrial process used to manufacture sulfuric acid is known as the contact process. Contact process. Let me quickly summarize the contact process. The raw materials used in the contact process are simply sulfur, oxygen, and water. That's if you are starting with what? Sulfur. Or it can also be sulfur 4 oxide, oxygen, and water if you are starting with sulfur 4 oxide. But let's start with sulfur. So there are 4 different stages. In the first stage, sulfur bonds in what? Oxygen in air to form what? Sulfur 4 oxide. Now in the second stage, the sulfur 4 oxide reacts with more oxygen in a reversible reaction to form sulfur 6 oxide. This reaction occurs at the temperature of about 150 degrees Celsius, but it occurs at a lower pressure of about 1 to 3 atm, and the catalyst used here is vanadium 5 oxide. Now in the third stage, the sulfur 6 oxide is dissolved in H2SO4. A little amount of concentrated sulfuric acid to form oleum, H2S2O7, and then the oleum is then dissolved, is then diluted with water to form concentrated H2SO4. Now the sulfur 6 oxide is not always dissolved in water in this stage 3 because the reaction is highly exothermic, and which makes it very dangerous. The high temperature will cause the acid to boil off and form acid fumes, which can be dangerous to the workers. That's why SO3 is not always dissolved directly in water to obtain H2SO4. Fine. So that's just a brief summary of the contact process. We're now asked to write a chemical equation for the reaction between ammonia and sulfuric acid. Write the chemical equation for the reaction between ammonia. Take note, this is ammonia and not ammonium hydroxide or aqueous ammonia. So which means that it will be what? NH3 gas. Remember, if you don't know your state symbol, don't bother. Plus what? Sulfuric acid is H2SO4 aqueous. That's the solution to give us what? Now, what will happen here? This H2SO4 will undergo ionization to form what? 2H plus and SO4 2 minus, because it's a strong acid. So these hydrogen ions will be picked up by the ammonia to form what? Ammonium ion. Is it not? So the ammonium ion will now combine with the sulfate ion to form ammonium tetraoxosulfate 6 or ammonium sulfate. How do we get that? Ammonium ion has a valency of 1. That's a charge of +1, while the sulfate ion has a valency of 2 or a charge of -2. So when they exchange their radicals, ammonium ion will pick up the valency of 2 from the SO4, and because ammonium is a radical, we have to put it in bracket and add 2 there, and then we have SO4 1, right? But since 1 is always invisible, we have it as NH42 SO4, which is what we have here. Alright, so let's continue. Question C says, when aqueous ammonia is added to aqueous ion 2 sulfate, a green precipitate is seen. This green precipitate turns red-brown at the surface. Now, when you have questions like this, the first thing I always advise students to do is to write out the chemical equation. The chemical equation will help you explain the chemistry behind the reaction or the process, right? So let's look at this. What would the chemical equation for this reaction look like? Aqueous ammonia is actually ammonium hydroxide. That's NH4OH plus ion 2 sulfate, that is FeSO4. Why is it FeSO4? This ion 2, Fe2 plus, and sulfate SO4 2 minus. So both of them have valencies of 2. So if they exchange their valencies, this will become Fe2 SO4 or bracket 2. Remember, SO4 is a radical. So by the time these two cancel out, this will give us FeSO4. Good. So what will be the product that will be formed here? The product will be formed through exchange of radicals. This NH4 plus, this OH minus, this Fe2 plus, this is SO4 2 minus. So the positive radical of one reactant will attract the negative radical of the other reactants, and vice versa. So this will be NH4 plus SO4 2 minus plus Fe2 plus OH minus. So by the time we exchange the radicals, this will give us NH4 2SO4 plus FeOH2. So I told that when aqueous ammonia is added to aqueous ion 2 sulfate, green precipitate is C. And the color green comes from which ion? Yeah, which metallic ion will form green color? The metal must be a transition metal for its ions to form green color, right? And the metallic ion that forms green precipitate is ion 2, right? So it means that this will be green precipitate, that's solid, while this one will be aqueous. And you can see that this reaction is a double decomposition or a precipitation reaction. And the precipitation reaction or a double decomposition reaction is a reaction in which two soluble reactants combine to form an insoluble substance by the exchange of radicals. So we are now asked to name the green precipitate, right? Which is from my equation on the screen, that's ion 2 hydroxide. Remember, you're asked to name ion 2 hydroxide, not the formula. Suggest why the green precipitate turns red-brown at the surface. Okay, let's go back to the question. This green precipitate, okay, turns red-brown at the surface. Now, which ion will form a red-brown color? If ion 2 forms green in solution, right? Or gives us a green ion, which other ion gives us a red-brown color? That would be ion 3, right? We are told that the precipitate turned red-brown, which means that the ion 2 in the precipitate changed to ion 3. And we are told at the surface, not all the precipitate, just at the surface. And so what will happen at the surface? It means that the surface of the precipitate is exposed to air, right? Exposed to the atmosphere. And what process occurs here from ion 2 to ion 3? That's an increase in oxidation state, which means that it is what? Oxidation. Oxidation has gone what? Occurred, right? So which means that the upper part of that precipitate that was exposed to the atmosphere has been oxidized by atmospheric what? Oxygen to ion 3. So the ion 2 ion in the precipitate is oxidized by atmospheric oxygen to ion 3 ion. This is how rusting takes place. When once the iron metal is exposed to moisture and oxygen, it will react to form ion 2. It will lose electrons, will oxidize to form ion 2 ion. Then the ion 2 ions will undergo further reactions with the atmospheric oxygen to form ion 3 ion, which leads to the formation of rust. Still, what happens when an excess of aqueous ammonia is added to the green precipitate? Now, when you add excess aqueous ammonia to the green precipitate, nothing will happen. Nothing will happen. The green precipitate will not dissolve. Ion 2 and ion 3 precipitates do not dissolve in excess aqueous ammonia. In other words, ion 2 hydroxide and ion 3 hydroxide do not dissolve in excess aqueous ammonia. So here, the precipitate, the green precipitate, remains insoluble. So what's happening here? The examiner is testing your knowledge of qualitative analysis tests for what? Ions. That's what this question is all about. So question 3D. Whether the ammonia reacts with oxygen as shown on the screen here, right? Now we're asked to calculate the oxygen at room temperature and pressure in dm cube that reacts with 4.80 dm cube of ammonia. Now this reaction here is also known as what? The oxidation of ammonia. And when it occurs in the presence of a catalyst like platinum rhodium at 700 degrees Celsius, it is called the catalytic oxidation of ammonia. It's used in industrial manufacture of triosylnitric 5 acid, HNO3 or nitric acid. That process is also known as the Oswald's process. The industrial manufacture of HNO3 is also known as the Oswald's process. Alright, but your scheme does not cover that, so that's just for your knowledge, right? So now coming back to the question, calculate the volume of oxygen at room temperature and pressure in dm cube that reacts with 4.80 dm cube of what? Ammonia. Now this question is on the user's law of combining volume, which says that when gases react, they do so in what? Volumes, which are in simple ratio to one another and to the product if what? Gaseous, provided the temperature and pressure remain what? Constant. So that's why I told to calculate this at room temperature and what? Pressure, that constant temperature and pressure. According to the user, we are told that 4 volumes of ammonia from the equation will react with 5 volumes of oxygen, right? It means that 4 dm cube of ammonia will react with 5 dm cube of oxygen, is it not? Remember, we are asked to calculate the volume of oxygen. And now to calculate the volume of oxygen that will react with 4.8 dm cube of ammonia. So if we solve for our x, it will be 4.8 dm cube of ammonia times 5 dm cube of oxygen all over 4 dm cube of ammonia. So this will go with this, and what will we have left? 4 will go here, 1 will go here, 1.2. 1.2 times 5. 1.2 times 5 dm cube will give us point 0 cube of oxygen. Alright, this next question is on bond energies. We are told that the chemical equation for the reaction can be represented as shown. Okay, blah blah blah. Use the bond energies in the table to calculate the energy change in kilojoules per mole, which occurs when 1 mole of ammonia reacts. Good. So we have the table here. So we have nitrogen hydrogen bond, oxygen oxygen double bond, nitrogen oxygen double bond, oxygen hydrogen single bond, right? And there are various bond energies. Now coming back to this equation here, how many nitrogen hydrogen single bonds do we have? Let's number them. We have 1, we have 2, we have 3. How many oxygen oxygen double bonds do we have here? We have 1. How many nitrogen oxygen double bonds do we have? We have 1 here. How many oxygen hydrogen single bonds do we have here? We have 2. 1, 2. Fine. Which means that here we have 4 of what? 3 nitrogen hydrogen what? Single bonds reacting with what? 5 of oxygen double bond to give us what? 4 of nitrogen oxygen double bond plus what? 6 of what? 2 oxygen hydrogen what? Single bond. So with this now, if we are to evaluate this further, we will see that this is what? 12. We have 12 nitrogen hydrogen what? Single bonds, right? And while here we have what? 12 oxygen hydrogen single bonds. Are we together? That's what we are now going to use to calculate our bond energy needed to break the bonds and energy needed to what? Form the bonds. Now the energies needed to break bonds, or what we call the bond breaking energy, BBE, are associated with the what? Reactants, because that's where the bond breaking occurs, and it is what? Endothermic. Why is it endothermic? Because bond breaking is an endothermic process. Energy is always taken in to break a bond, whereas bond forming is an exothermic process. Energy is always given out when a bond is what? Formed. Before 2 atoms can form a bond, they must lose something, they must come to a compromise, right? So that compromise is the loss of heat. So the energy released when bonds are formed is called the bond forming energy. That's which is associated with the what? Product. Fine. And it's what? Exothermic, as I've explained what? Earlier. What are the bond breaking energies now? The bond breaking energies here are 12 nitrogen hydrogen bonds, right? And 5 oxygen double bonds. So it will be 12 times what's the value of the nitrogen hydrogen bond. Remember, in this table you are given the bond energies as absolute what? Values, not as negative or positive, because it can be anywhere. So it now depends on where they will be what used. If they are found in the reactant, then they will appear as positive. If they are found in the product, it can be used as what? Negative if necessary, right? So there will be 3, 9, 1, right? And this one is what? 5 times oxygen double bond is 498. So if we use our calculators to calculate this gives us 4692, while this gives us 2490. If we add up these two, that will give us the 2817. So the answer is what? 7182 kilojoules. Remember, in the table you are given the values as kilojoules per mole, and from the equation of reaction provided from what we have here, you can see that we have 12 moles of nitrogen hydrogen bonds involved in this reaction on the reactant side, and 5 moles of the oxygen what? Double bond involved in the reaction on the reactant side. So by the time we multiply 12 moles by 391 kilojoules per mole and 5 moles by 491 kilojoules per mole, and then add everything together, we obtain 7,182 kilojoules, not kilojoules per mole. Fine. So for the energy release when bonds are formed, that's the bond forming energy. What are the bond forming energies here? That's 4 nitrogen oxygen bonds. Yes. Is it not? Yes. That's 4 nitrogen oxygen bonds and 12 oxygen hydrogen single bonds. 4 nitrogen oxygen double bonds and 12 oxygen hydrogen single bonds. So this will be 4 moles times 587. That's the value of the nitrogen oxygen double bond, and this will be 12 times 464, which is the value of the oxygen hydrogen single bond. So you evaluate this, you obtain 2, 3, 4, 8. Well, this one gives us 5, 5, 6, 8. If you now add up these two together, we have 6, 10 plus 1, 11 plus 1, 8 plus 1, 9, 10, 7, 9, 1, 6. So answer is what? 7916 kilojoules. So the energy change when 1 mole of ammonia reacts, 1 mole, fine. When 1 mole of ammonia reacts, now the energy change, like I explained earlier, is given as what? Bond breaking energy minus bond forming energy, or bond breaking energy plus bond forming energy. Now you use this value, use this formula here when you use the absolute values of the bond energies like this in your calculations. You can see when I calculated my bond forming energy here, I did not add the minus sign, I just used them as the absolute value, because this is the formula I'm going to use. But if I were to use bond breaking energy plus bond forming energy, then I will use this as negatives. That's 4 times minus 587 and 12 times minus 464. Are we together? So this would have given me minus 7916. So we have to be careful when using any of these two formulae. Here I repeat, when you are using this BBE minus BFE, you use the absolute values of the bond energy as given. You don't add any sign, right? Just calculate everything, sum up everything, bond breaking energy, bond forming energy, and then subtract the bond forming energy from the bond breaking energy. That's all. If you want to use this, then you must convert the bond forming energies to what? Negative values. You must use the negative values of the bond forming energy. Alright. So the bond breaking energy that we obtained is 7182, while the bond forming energy that we obtained is 7916. So if you subtract this, we obtain minus 734 kilojoules, right? But that is not our answer, because we are told to calculate the energy change when 1 mole of ammonia reacts. If you go back to the equation of reaction, how many moles of ammonia reacted in this equation of reaction? Let's come back here. 4, is it not? 4 moles of ammonia reacted. 4 moles of ammonia reacted in this equation, which means that this energy change is the energy given off when 4 moles of ammonia reacts, is it not? So now to calculate the energy change when 1 mole of ammonia reacts, okay, let's do this. So 4 moles of ammonia will give us minus, generate minus 734 kilojoules, right? Then 1 mole of ammonia generate what? X. So our X now will be what? Minus 734 over 4, which gives us minus 183.5 kilojoules per mole. So the answer here is minus 183.5 kilojoules per mole. So that brings us to the end of the solution to question 3 of the October-November 2019 Cambridge IGCSE Chemistry Paper 4. If you know you learned anything from this tutorial, hit the like button and leave a comment. Also, if this is your first time here, subscribe to our channel and turn on the notification bell to always stay updated with our new uploads. And I can assure you, you will not regret doing that. A wise man once said, mistakes were meant to be made. That's why pencils were made with erasers. So continue learning from your mistakes till I see you when I'll see you.